Hello students. So today in this class we are going to discuss about gravitational potential. Gravitational potential and gravitational potential energy. Gravitational potential energy. So let us consider that there is a mass. There is a mass. This you can say it is a source mass. Because of source mass, if any object of mass m is brought near, it will experience a force because this source mass is creating a field. Because of that, there is a force on any object kept nearby. Now, what is the concept of gravitational potential? So, let us say that initially the separation between them is very large. Let us say the separation between these two masses, x is infinity. Now you want to bring that mass at a distance of x equal to r. So when you are bringing it from infinity to this point, you have to do some work, right? So work done in bringing the small mass or any other mass from infinity to this location r divided by that mass, that is called the potential. Potential may be written by the symbol V. Okay, so potential at that given location, actually it is the change of potential that we can say as delta V. But here we are going to consider potential at infinity to be 0. That is why when you are taking potential at this point, you can define this as just the potential work done from moving the particle from infinity to that location per unit mass. Here we are keeping potential at infinity to be 0. Okay. Now let's understand how to calculate the work done, right? So for that you have to take a particular point, any instantaneous point you take. Here you assume that the particle is at this instant while you are moving it. So when you are moving it, the force of gravitation is acting in this manner, right? This is the force of gravitation force, and you have to bring it gradually or slowly. So you need to keep an external force definitely in this direction. The force that you are going to keep is opposite of the gravitational force, otherwise it may accelerate, right? So you don't want to accelerate the particle, right? So the force which you are applying is opposite of the gravitational force, so minus of that. Okay, anyway, now let us substitute the value of gravitational, and this work done we want to calculate. Work done by which? By external force. Okay, so work done calculation will be integration of external force, right, into displacement. So let us do that. Displacement dot product, and here you can see that this force, gravitational force and external force are equal in magnitude. So magnitude wise you can write it as but remember here you should give some direction of the force also, because your force is a vector, so you have to give some direction. If you take gravitational force as minus g mm by x square, right, because minus represent attractive force, so here minus of this will become plus, so g mm by x square. Now let us flip this gmm by x square, right, into dx, and you are going from infinity to that location r. So let's integrate this. So it will become gmm 1 by x square, integration is minus 1 by x, and you are going from infinity to r. Substitute the upper limit, minus gmm by r. Okay, so this is the work done, and from infinity to that point, right? So potential at that point will be defined as minus gmm by r divided by m. So this is the potential, minus gmm, small m is no more there, right, by r. So this formula is representing the work done per unit mass. Of course, this small mass is taken as the test mass, right? This is small mass. You can see that it is a test mass. It's a very, very small mass, which is not affecting the source mass. Source mass is rather very big in size. Source mass will be very big, right? Test mass will be very, very small. So you can consider the size of this, right? Okay, so this is the potential formula. Then potential energy, from here itself we can do it, potential energy calculation. So this is also work done by external force, right? That is nothing but the potential energy, or of course you may say that is the change of potential energy. Work done by the external force is change of potential energy. So we have taken potential energy finally at that location r minus potential energy at infinity, but here we are keeping this potential energy to be 0. So this work done formula which you have got, that is the potential energy minus gmm by r. So this is the equation of the potential energy at that location. The bracket r represents that potential energy function. Here you may also write v as vj function of r. So minus gm by r. Many textbooks you will see it is written like that. Okay, so it doesn't matter, how you write, but that's the potential and potential energy function, right? Okay, then next we are going to see about the calculation of potential and potential energy. So potential and potential energy, both are scalar quantities. First of all, we should note that both are scalar quantities. And if you take only about potential, so potential is a property of source mass or masses, because there can be many other source, right? So this is property of the source because it is created due to this source. But potential energy is property of the system. It is a property of system of masses. System of masses means there will be many mass, and it's an interaction between all those masses. It is an interaction between all the masses, right? Now let's take example. How do we calculate? And unit of this potential, as we can see, it is joule per kg, right? And potential energy is of course energy, which is joule, SI unit. Okay, so if there is a particle, another particle, so many particles are there. Let's say mass m1, m2, m3, so many particles. You can say system of particles. So if there is a particular point, let's say O, which is at a distance of r1, second particle is at a distance r2, third particle distance r3, like that. So many particles may be there. So the net potential at O is equal to total potential is the sum of potential due to 1, potential due to 2, potential due to 3, and so on. We can just add. So minus Cm m1, first mass is m1, minus Cm1 by r1, minus Cm2 by r2, minus Cm3 by r3, like so on. You have to keep on adding these potentials, right? This is how we can calculate potential due to a system of particles. Then similarly, potential energy. Now coming to the calculation of potential energy, this is mass m1, this is mass m2, this is mass m3, and so on. So when you want to calculate potential energy of a system of particles, that net potential energy is the interaction between two masses. So you have to group potential energy 1, 2, potential energy 1, 3, potential energy 1, 4, like that. First you make group taking 1 as a common, then you can take 2, 2, 2, 3, 2, 4, like this. Then you can take 3 can be also taken with 3, 3, 3, 3, 4, like that. 3, 5. You have to also, when the particle, when you are taking 1, 1, this 1, 1 also you can add here. 1 can also interact with itself. This is called self potential energy. Okay, U11, U22, U2, U33, these are called self potential energy. That also we will discuss, self potential energy. Okay, so in calculation of self potential energy, of course, here if it is a particle, just a single particle or point mass, then we may not consider the self potential energy. But if the mass is distributed, right, like a sphere or some other distribution, then we need to consider self potential energy, because to build up that charge, you are gradually bringing small charge to build up that single charge. So in case of particles, self potential energy need not be considered. In case of single particle, self potential energy is not considered. Okay, that means you can remove this. In this particularly, you can definitely remove U11, U22, U33 can be removed from this calculation. But in case if this is like, let's say, solid spheres are there, then definitely you have to consider all those things, right? Okay, then next. So this is the concept of potential and potential energy. Now we may write some important formulas for potential for different type of objects, right? So let us take, for example, potential of a circular ring. Potential of a circular ring. So consider there is a ring here. This is a ring. The radius of this ring is r. This O is the center, r is the radius. And on this axis, you choose a point P, which is at a distance of x from here. Now we can calculate the potential at this point P as minus Gm by root under r square plus x square, which is nothing but this distance. So this distance is root under r square plus x square. Okay, because each point on this ring is same distance, so we are actually adding up by doing the summation, right? We are actually calculating the small potential first due to this small mass dm, and this distance is same, so potential is minus c dm by root under r square plus x square. And we are integrating it. Remember, when you are integrating it, this distance is not changing, so integration of dm is giving the total mass, and here is the total mass of this ring. Okay, then let's move to the next. What about if we have a spherical cell? What happens to the potential inside? So if you consider spherical cell, spherical cell means inside completely it is hollow. All the mass is present on the surface of the sphere, and let's say radius is r. So potential inside and potential outside. So any point, let's take inside the distance r. So for r less than or equal to r, the potential is going to be minus Gm by capital R. This is going to be constant that we have to note. And for points outside, the potential is going to be minus Gm by R. That means if you take point outside, this distance r, then it is varying like a point mass, right? If you take points outside, then it looks like the whole mass of the cell is concentrated at the center. And you may try to draw the diagram of the potential versus R also. So when you draw this diagram, what do you get is, let us say I am just drawing the magnitude of this potential. Otherwise I have to take the graph in negative. Let's say that I am drawing the magnitude of this potential. So Gm by R, it will be, right, first it will be constant. It will be constant like this. And then I have to make it inversely proportional to R like this. Okay. So up to the radius it is constant. If you exactly want to draw the diagram without considering the magnitude, you may do that also. V versus R. So only thing is that it is constant in negative direction like this up to this R. After that it may go like this. Okay. So here without magnitude and with magnitude you can understand that. Okay. Then next, what about if you consider potential due to a solid sphere? This is important result we should know. Solid sphere means this everything, the big within a sphere you can choose, right? So big sphere, solid sphere, material is present throughout the volume. Okay. Solid sphere. So let us say this solid sphere, radius of this solid sphere is r. Take any point inside and take any point outside. Okay, so first we will write for r less than equal to capital R. How does this potential is given by, what is the formula for their potential? So note that we can write this as, here capital M is the mass of the total, right? Minus Gm by R, 3 by 2 minus x square by 2 r square. Okay, this formula we can use to calculate the potential for any points inside. Okay, right? And you can note here at the center O, at center x is equal to 0, potential will become minus gm by r into 3 by 2, okay, which is 1.5 times. And at surface x is equal to capital R, potential will become, because x is equal to r, so 1 by 2, 3 by 2 minus 1 by 2, so 1 will come, so minus Cm by r into 1. So note that the potential at the center is 3 by 2 times potential at the surface. Yes, so potential at the surface and potential at the center you consider. So potential at the center is 3 by 2 times potential at the surface. Okay, right? So if you see the graph, again you can see the graph of the magnitude. Most of the textbook they may give, or that is the negative direction of that. You may draw that diagram itself by taking that as negative, or you may draw that, doesn't matter. Let us say I draw this as the negative potential. Of course potential is going to be negative because this is the negative direction we are choosing, isn't it? Right? So this is suppose potential versus R. This direction is negative potential, so the graph that is going to happen, whatever graph you will be seeing, you will see that potential will go like this up to that point R. After that point, this is like this. Okay, so this is the center, x is equal to 0, right? Or r is equal to 0. This point r is equal to 0. So here it is minus 3 by 2 gm by r. At the surface here, potential is minus gm by r. Okay, but after the surface, that means for r greater than r, that is same as the point mass, minus gm by r. So this is the potential variation. That's how you can see that there is a change of shape happening at this point. You have to note that the shape of this graph is converting from concave to convex at this point. So at r is equal to capital R, double differentiation, the square v by dr square will be 0. That's called point of inflation. So that is there. Sometimes they may ask because their shape is changing, right? Because just before that point the shape is concave here. After that shape becomes convex. Okay. So this is an important result, right? Okay. Then let us go to the next. Next we can see the relationship between potential, relation between field and potential. Field means E, potential is V. Same way we can understand relation between force and potential energy. So two things we can see here. Let's understand field and potential relationship. So field in terms of vector can be given as minus 2v by 2x I cap minus 2v by 2y j cap minus 2v by 2z q cap. And in general we can write this also minus del vector of v. Okay. This is how we can write potential. And exactly same way is the relation between force and energy. Force is equal to minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou z k cap. And this force vector can also be written as minus del vector of u. Okay, so we need to understand here one important thing, that what is the partial differentiation means and how to solve this partial differentiation. Partial differentiation is same as differentiation. The only thing that we should note is that it's a function. For example, let's say v can be a function of x, y, z. For example, suppose v is x square plus y square plus z square, and they ask you to find electric field at some point. So how do you calculate electric field? So electric field, when you are calculating, you are doing partial differentiation of v with x I cap minus partial differentiation of v with y j cap minus partial differentiation of v with z k cap. So what is this partial differentiation? It is differentiation only. So you are differentiating this whole term, right? X square plus y square plus z square with respect to x. But remember, when you are differentiating with x, y and z are constant. When you keep y z constant, that differentiation of y square z square will become 0. So x square differentiation is just 2x. Okay. Same manner, partial differentiation of v with y will give 2y, and partial differentiation of v with z will give 2z. Right? And then you can just substitute here. So electric field in this example will get as minus 2x I cap minus 2y j cap minus 2z k cap. Right? So, and different points you can substitute values. Suppose they have given you x, y, z, you may substitute and calculate. This is just example to understand the calculation of field from potential, right? Or exactly same way force you can calculate from energy, potential energy. Also note that if the potential this calculation has to be done in one direction or one dimension, you can simply write field as minus dv by dr. Okay, and in 3 dimension you can also write, already I am told that, partial differentiation. But sometimes dv can be brought this side and you can write minus cdr. But here in vector form you have to take this dot product. Okay, this is important thing. In 3 dimension, this generally you can apply like this. That's why when you are going to integrate this both sides, dv vector, sorry, this dv vector is not there. This dv that we are saying is change of potential, right? So this dv is just change of potential. dv is not a vector, change of potential. So integration, when you are doing dv integration, you have to integrate this minus e vector dot dr. So that is delta v, change of potential, that is written as minus integration e dot dr vector. Here right hand side dot product of vectors is there, which is a scalar only. Same manner, this force F in 1 dimension, we can write it as du by dr. Again, when you bring this side, so du becomes minus F vector dot dr. And when you integrate this, both sides you can integrate also. First note this du is equal to this. Then when you integrate it, du is equal to minus F dot dr. So this will become delta u is equal to minus F dot dr. Okay, right? So here you need to note one thing, that this is the change of potential energy. Delta u is change in potential energy, change in gravitational potential energy, and this is equal to minus of, here F is the gravitational force. This is the work done by gravitational force. Work done by gravitational force. Okay, which is a conservative force. Which is a conservative force. This rule is valid for in general for any conservative force. Okay, change of potential energy is equal to minus of work done by conservative force. So with these definitions we can work out problems. Thank you for your attention.